Now we're going to go over the distribution of the difference between two sample means. I drew it out prior to this lecture because it takes a long time and there's a lot that can go wrong. So let's take a look at what's going on here. We have a sample 1 and a sample 2. Those two samples can have their own distribution, their own separate means, their own separate standard deviations, their own shapes. They can be whatever they want. What we're trying to do is estimate the difference between these two means, mu1 minus mu2. We're trying to estimate this quantity right here, mu1 minus mu2. So what we do is we take a sample of data, and we end up with a sample mean for group 1 and a sample mean for group 2. That sample mean, if it meets the central limit theorem conditions, that will follow a normal distribution. Sample 2, if that meets the conditions, that will also follow an approximate normal distribution. The centers of those two distributions are exactly the same. Mu1 equals mu x bar 1. Mu2 equals mu x bar 2. But we're not analyzing those distributions. What we're doing is from that sample mean, we take a sample 1 and we take our sample 2 and we subtract them and end up with this black dot right here. This represents the difference between two sample means. And we can repeat this process over and over. Take another sample mean from group 1, another sample mean from group 2, and end up with a different difference between two means. We can repeat that process over and over and over and over and over again. And what we end up with is this distribution down here. This distribution is called the difference between two sample means. The distribution of the difference between two sample means. And we'll notice a couple things about it. Now, I may not have drawn it perfectly to scale, but the distribution of the difference between two sample means has a bigger spread than the individual sampling distributions. The sampling distribution of x bar 1 and the sampling distribution of x bar 2. The spread of x bar 1 minus x bar 2 will have a bigger spread. And one way to think about that, because it may not be intuitive, right? You think, well, x bar 1 minus x bar 2, you're subtracting them. Maybe they should have a smaller spread. But no, think about it like this. There's variability associated with your first sample. There's variability associated with your second sample. Now that we're looking at the difference between your two sample means, we're essentially combining those two variabilities together. That's essentially what's going on here. This represents the standard deviation of the difference between our two sample means. S sub x bar 1 minus x bar 2. It's your standard error. And if we look at your standard error formula, it's essentially taking your first spread, the spread of x bar 1, and the spread of x bar 2, and it's adding them together. That's essentially what's going on here. It's essentially adding your two spreads together. The spread of your first group plus the spread of your second group. Now that you're combining those two groups together by looking at the difference between your two means, you have to worry about the variability associated with your first sample and your second sample. Your first sample mean and your second sample mean. So this formula right here will be our new standard deviation or standard error. What's also important to notice is that the center of this distribution, which is denoted by this orange line, mu x bar 1 minus x bar 2, that center equals the difference between your two population means that you're interested in. So if we can estimate mu x bar 1 minus mu x bar 2, that orange line, what we've actually have learned about is mu 1 minus mu 2. So this will be the distribution that we are looking at when estimating the difference between our two means. Just like we learned before when we estimated a single mean, this distribution will follow a t-distribution. But if we remember, our t-distribution isn't a single distribution, it's an infinite amount of distributions. It depends on the concept of degrees of freedom. Previously, our degrees of freedom was n minus 1. But wait a second. Now we have 2 samples of data. But wait a second. Now we have 2 samples of data. So we can't use n-1 right here because we have 2 samples of data. Let's go figure out then how many degrees of freedom we should use to find the probabilities and percentages associated with the t-distribution we'll be interested in. To recap, so you have things in your notes, the spread of the difference between your 2 sample means is actually going to be larger than the individual sample mean spreads. And it's denoted by the notation and formula right here. It's essentially adding your 2 spreads together. The degrees of freedom that we'll be using for our t-distribution, while there's different ways to go about it, what we're going to be looking at the smallest sample size minus 1. So think of this, df will equal n smallest minus 1. Now this is a conservative approach. There are other estimates of your degrees of freedom that you could and maybe even should be using. However, for this introductory class, I think it's best for us to go with the mindset of something that's attainable to us. And this is accomplished by looking at the smaller sample size minus 1. It's going to be the conservative approach. We may not get the most precise estimates, but it's not going to be very likely that we're going to be incorrect, right? We're going to go with a conservative approach when we find our probabilities and percentages associated with the t-distribution.